perfect number. Write the function nth perfect number that takes a non-negative integer n and returns the nth perfect number starting at 0. A number is perfect if it is the sum of its positive divisors less than itself. So 6 is perfect because 6 is 1 plus 2 plus 3. So it's less than itself, so we're not adding in 6. And 28 is perfect because it's, the sum of those divisors. Then 496, and finally 8128. There's actually a faster version, but let's skip that for now and just do the slower version first. Okay, nth perfect number. And just for kicks, let's go ahead and test nth perfect number. And to begin with, we're not correct because the 0th perfect number turns out, oddly enough, not to be 42. Okay, let's get into this. So it's going to be suspiciously similar to all our other nths, right? You have the number that you've found so far, your current guess. As long as you haven't found enough, keep guessing. If it is a perfect number, we found another one, and when we found as many as we need, go ahead and return that one. Okay, so really the work is in is perfect number. So we'll go ahead and define is perfect number then. So now a number is perfect if it's the sum of its divisors between 1 and itself. So the total, let's call it the, the divisor sum is initially 0. We're going to count up the divisor in range up to n, but starting at 1, okay? And we'll say if n mod divisor is 0, that means we found a divisor, and we'll say divisor sum plus equals that divisor. So we're adding up all the divisors. So we walk through all the numbers from 1 to n, not including n, which is critical. We checked if we found a divisor, and then we just added it in. It's a perfect number if the divisor sum is double equal to n, then we'll return true, else we'll return false. That's the test, and when we run, we see that it's testing all, and it's really, really slow, and it's slow, but it worked. Okay, and actually, I don't like this form. We've talked about this before. I prefer this form. Not only I prefer, you should do this form. Just return that. The point being, when this is true, we return true, and when this is false, we return false. So just return this, meaning that line 112 is the exact same as these 4 lines. So let's just get rid of those 4 lines. And we'll run this again, and it's still really, really slow, and it's painfully slow, but it works. Okay, so now we want to make it not so slow. And for that, we realize exactly the same observation we made back when we were doing faster is prime, which was to say that we only have to go up to the square root. Okay. By the way, we could also do the even thing to make it even faster still, but the chief thing we're going to do is only go up to the square root. So let's actually copy this, leave our slow version, and modify it for a fast version. In the fast version, you only want to go up to and including the max factor. And as we find divisors, we have to add them in. But this isn't going to work. Actually, it's going to be fast. It's going to fail. Let's watch it be fast and it fails. And the reason, so nth perfect number of 0, we said is 6. And we found that 1 is perfect. Yikes. Okay. There's a couple mistakes in here. But the key one is this. We observe that we're only going to find the divisors up to the square root this way. We're not going to find any divisors after the square root. But that's okay. Divisors come in pairs, right? So all we have to do is add into the divisor sum, if you want, the other divisor, which is just n divided by the divisor we found. Okay. Now this is closer, but it's still going to have a problem. When you find 1, you're also going to add in n. So for that, there's a couple things we could do. We could simply go up to see if it matches 2n, because we'll get an extra n in there. Or we could start our divisor sum at 1 and start our counting at 2. Either of those would actually suffice. It's not clear which way is better. Let's actually do it this way. Start at 0, and let's do 2n. Okay, and that's close. We still have this weirdness about 1. So here we'll say simply if n is less than or equal to 1, return false. And now we're zippy quick. That was dramatically faster. To show you again, let's just do that so that we use the slower one. Here's your slower one. That's very clean logic, only sadly very, very slow. And here's your faster one, which just zips along. So when we're testing 8128, to make it really clear, the square root of 8128, oops, if I know how to type, the square root of 8128 is only about 90. So instead of going up to 8100 times, we only have to do this 90 times, which is naturally quite a bit faster. In any case, theirs is perfect number, there's nth perfect number, and we are done with check 2. Now, you should be able to reproduce all these functions on your own. Do not skip that last step. Please move on to it. Start from scratch, work your way through check2.py, and write these functions. Good luck. Have fun.